Hello everyone, this is an audio recorded lecture from class 12's NCERT on the topic coordination compounds chemistry. In the previous unit, we have learned that the transition metals form a large number of complex compounds in which the metal atoms are bound to a number of anions or neutral molecule by sharing of electrons. In modern terminology, such compounds are called coordination compounds. The chemistry of coordination compounds is an important and challenging area of modern inorganic chemistry. New concepts of chemical bonding and molecular structure have provided insights into the functioning of these compounds as vital components of biological system. Chlorophyll, hemoglobin, and vitamin B12 are coordination compounds of magnesium, iron, and cobalt, respectively. Variety of metallurgical processes, industrial catalysts, and analytical reagents involve the use of coordination compounds. Coordination compounds also find many applications in electroplating, textile dyeing, and medicinal chemistry. Now, first topic in coordination chemistry is Werner's theory of coordination compounds. Alfred Werner, a Swiss chemist, was the first to formulate his idea about the structure of coordination compounds. He prepared and characterized a large number of coordination compounds and studied their physical and chemical behavior by simple experimental techniques. Werner proposed the concept of primary valence and a secondary valence for a metal ion. Binary compounds such as CrCl3, CoCl3, or PdCl2 have primary valence of 3, 2, and 2 respectively. In a series of compounds of cobalt 3 chloride with ammonia, it was found that some of the chloride ions could be precipitated as AgCl on adding excess silver nitrate sodium nitrate solution in cold, but some remained in solution. For example, 1 mole COCl3.6NH3, which is yellow in color, gives 3 mole of AgCl. 1 mole of COCl3 5NH3, which is purple in color, give 2 mole of AgCl. 1 mole of COCl3.4NH3, which is green in color, gave 1 mole of AgCl, and 1 mole COCl3.4NH3, which is violet in color, gave 1 mole of AgCl. These observations, together with the result of conductivity measurement in solution, can be explained if 6 groups in all, either chloride ions or ammonia molecule or both, remain bonded to the cobalt ion during the reaction, and the compounds are formulated as shown, where the atoms within the square brackets form a single entity which does not dissociate under the reaction conditions. Werner proposed the term secondary valence for the number of groups bound directly to the metal ion. In each of these examples, the secondary valence are 6. Note that the last two compounds in the table have identical empirical formula COCl3.4NH3 but distinct properties. Such compounds are termed as isomers. Werner in 1898 propounded his theory of coordination compounds. The main postulates are: in coordination compounds, metals show two types of linkage, primary and secondary. The primary valences are normally ionizable and are satisfied by negative ions. The secondary valences are non-ionizable. They are satisfied by neutral molecule or negative ions. The secondary valence is equal to the coordination number and is fixed for a metal. The ions or groups bound by the secondary linkage to the metal have characteristic spatial arrangement corresponding to different coordination numbers. In modern formulation, such spatial arrangement are called coordination polyhedra. The species within the square bracket are coordination entities or complexes, and the ions outside the square brackets are called counter ions. He further postulated that octahedral, tetrahedral, and square planar geometrical shapes are more common in coordination compounds of transition metal. Thus, CONH3 whole 6 3 positive is tetrahedral entity, while NiCO4 and PtCl4 2 negative are tetrahedral and square planar respectively. Difference between a double salt and a complex. Both double salt as well as complex are formed by the combination of two or more stable compounds in stoichiometric ratio. However, they differ in the fact that double salt such as kernelite, that is KCl.MgCl2.6H2O, and more salts, that is FeSO4.NH4 whole twice 2 SO4.6H2O, potash alum, that is KAlSO4 whole twice dot 12H2O, etc., dissociate into simple ions completely when dissolved in water. However, complex ions such as FeCN6 4 negative of K4 FeCN6 do not dissociate into Fe2 positive and Cn negative ions. Next topic is definition of some important terms related to coordination compounds. First is coordination entity. A coordination entity constitutes a central metal atom or ion bonded to a fixed number of ions or molecules. Next is central atom. In a coordination entity, the atom or ion to which a fixed number of ions or groups are bounded in a definite geometrical arrangement around it is called the central atom or ion. Next is ligand. The ion or molecule bound to the central atom in the coordination entity are called ligands. These may be simple ions such as Cl negative, small molecules such as H2O or ammonia, larger molecule such as H2N, CH2, CH2, NH2, or even macromolecules such as protein. When a ligand is bound to a metal ion through a single donor atom, as with chlorine, water, or ammonia, the ligand is said to be unidendant. When a ligand can bind through two donor atoms, as in ethane 1,2-diamine or oxalate, the ligand is said to be didendate. And when the several donor atoms are present in a single ligand, as in NCH2CH2 NH2 3, the ligand is said to be polydendant. EDTA is an important hexadendate ligand. It can bind through 2 nitrogen and 4 oxygen atoms to a central metal ion. When a di or polydendant ligand uses its 2 or more donor atoms simultaneously to bind a single metal ion, it is said to be a chelate ligand. The number of such ligating groups is called the denticity of the ligand. Such complexes, called chelate complexes, tend to be more stable than similar complexes containing unidendant ligands. Ligands which has two different donor atoms and either of two ligates in the complex is called ambidendant ligand. Example of such ligands are the NO2 negative and SCN negative ions. NO2 negative ion can coordinate either through nitrogen or through oxygen to a central metal atom. Similarly, SCN ion can coordinate through the sulfur or nitrogen atom. Next is coordination number. The coordination number of a metal ion in a complex can be defined as the number of ligand donor atoms to which the metal is directly bonded. For example, in the complex ion PtCl6 2 negative, the coordination number of platinum is 6. Similarly, in the complex ion FeC2O4 3 negative, the coordination number of Fe is 6. It is important to note here that coordination number of the central atom ion is determined only by the number of sigma bonds formed by the ligand with the central atom. Pi bonds, if formed between the ligand and the central atom, are not counted for the purpose. Next is coordination sphere. The central atom and the ligand attached to it are enclosed in square bracket and is collectively termed as coordination sphere. The ionizable groups are written outside the bracket and are called counter ions. Next is coordination polyhedron. the spatial arrangement of the ligand's atom, which are directly attached to the central atom, defines a coordination polyhedron about the central atom. The most common coordination polyhedra are octahedral, square planar, and tetrahedral. These are the shapes of different coordination polyhedra. M represents the central atom and L a unidendent ligand. Next is oxidation number of central atom. The oxidation number of the central atom in a complex is defined as the charge it would carry if all the ligands are removed along with the electron pair that are shared with the central atom. The oxidation number is represented by a Roman numeral in parentheses following the name of the coordination entity. Next is homoleptic and heteroleptic complexes. Complexes in which a metal is bound to only one kind of donor group are known as homoleptic. Complexes in which a metal is bound to more than one kind of donor group are known as heteroleptic. Next is nomenclature of coordination compounds. It is important in coordination chemistry because of the need to have an unambiguous method of describing formulas and writing systematic names. Particularly when dealing with isomers, the formulas and names adopted for coordination entities are based on the recommendation of the International Union of Pure and Applied Chemistry, that is IUPAC. Formulas of mononuclear coordination entities. The formula of a compound is a shorthand tool used to provide basic information about the constitution of the compound in an concise and convenient manner. Mononuclear coordination entities contain a single central metal atom. The following rules are applied while writing the formula. First, the central atom is listed first. Second, the ligands are then listed in alphabetical order. The placement of a ligand in the list does not depend on its charge. Third, polydendent ligands are also listed alphabetically. In case of abbreviated ligands, the first letter of the abbreviation is used to determine the position of the ligands in alphabetical order. Fourth, the formula for the entire coordination entity, whether charged or not, is enclosed in square bracket. When ligands are polyatomic, their formulas are enclosed in parentheses. Ligands abbreviation are also enclosed in parentheses. Fifth, there should be no space between the ligand and the metal within a coordination sphere. Sixth, when the formula of a charged coordination entity is to be written without that of the counter ion, the charge is indicated outside the square bracket as a right superscript with the number before the sign. Seventh, the charge of the cation is balanced by the charge of the anion. Next is naming of mononuclear coordination compounds. The name of the coordination compounds are derived by following the principle of additive nomenclature. Thus, the group that surround the central atom must be identified in the name. The rules are used The following rules are used when naming coordination compounds. First, the cation is named first in both positively or negatively charged coordination entity. Second, the ligands are named in an alphabetical order before the name of the central ion. Third, name of the anionic ligand end in O. Those of neutral and cationic ligands are the same except aqua for water, amine for ammonia, carbonyl for CO, and nitrosyl for NO. While writing the formula of coordination entity, they are enclosed in brackets. Fourth, prefix mono, di, tri, etc. are used to indicate the number of individual ligands in the coordination entity. When the name of the ligands include a numerical prefix, then the term bis, tris, tetrakis are used. The ligand to which they refer being placed in parentheses. Fifth, Oxidation state of the metal in cation, anion or neutral coordination entity is indicated by Roman numeral in parentheses. Sixth, if the complex ion is a cation, the metal is named same as the element. For example, cobalt in a complex cation is called cobalt and platinum is called platinum. If the complex ion is an ion, the name of the metal ends with the suffix "ate". For example, cobalt in an complex anion is called cobaltate. Seventh, the neutral complex molecule is named similar to that of the complex cation. For example, if we have to name CrNH3 3H2O3 square bracket closed Cl3, it is named as triamine triaqua chromium 3 chloride. Explanation. The complex ion Explanation. The complex ion is inside the square bracket which is a cation. The amine ligand are named before the aqua ligands according to alphabetical order. Since there are 3 chloride ions in the compound, the charge on the complex ion must be +3. From the charge on the complex ion and the charge on the ligand, we can calculate the oxidation number of the metal. In this example, all the ligands are neutral molecule. Therefore, the oxidation number of chromium must be the same as the charge of the complex ion, that is +3. Next is isomerism in coordination compounds. Isomers are two or more compounds that have the same chemical formula but a different arrangement of atoms. Because of the different arrangement of atoms, they differ in one or more physical or chemical properties. Two principal types of isomerism are known among coordination compounds, each of which can be further subdivided. A. Stereoisomerism, which has two parts, geometrical isomerism and optical isomerism. Next is structural isomerism, which has four parts, linkage isomerism, coordination isomerism, ionization isomerism, and solvate isomerism. Stereoisomers have the same chemical formula and chemical bonds, but they have different spatial arrangement. Structural isomers have different bonds. A detailed account of these isomers are given below. This type of isomerism arises in heteroleptic complexes due to different possible geometric arrangement of the ligands. Important examples of this behavior are found with coordination number 4 and 6. In a square planar complex of formula mx2l2, X and L are unidendant. The two ligands X may be arranged adjacent to each other in a cis isomer or opposite to each other in a trans isomer. Other square planar complex of the type MABXL, where ABXL are unidendants, show 3 isomer, 2 cis and 1 trans. You may attempt to draw these structures. Such isomers is not possible for a tetrahedral geometry, but similar behavior is possible in octahedral complexes of formula mx2l4, in which the two ligands X may be oriented cis or trans. This type of isomerism also arises when didendant ligands are present in complex of formula mx2ll2. Another type of geometrical isomerism occur in octahedral coordination entities of the type Ma3B3. Three donor atoms of the same ligands occupy adjacent position at the corner of an octahedral face. We have the facial isomer. When the positions are around the meridian of the octahedron, we get the meridional isomer. Next is optical isomerism. Optical isomers are mirror images that cannot be superimposed on each other. These are called as anisomers. The molecules or ions that cannot be superimposed are called chiral. The two forms are called dextro and levio Depending upon the direction they rotate the plane of polarized light in a polarimeter. Optical isomerism is common in octahedral complex involving didendant ligand. In a coordination entity of the type PTCl2 En2 square bracket close 2 positive, only the cis isomers show optical activity. Next is linkage isomerism. It arises in a coordination compound containing ambidendant ligand. A simple example is provided by complexes containing the thiocyanate ligand NCS negative, which may bind through the nitrogen to give MNCS or through sulfur to give MSCN. Jorgensen discovered such behavior in the complex CONH3,5NO2Cl2, which is obtained as the red form, in which the nitrite ligand is bind through oxygen, and as the yellow form, in which the nitrite ligand is bound through nitrogen. Next is coordination isomerism. This type of isomerism arises from the interchange of ligands between cationic and anionic entities of different metal ions present in a complex. Next is ionization isomerism. This form of isomerism arises when the counter ion in a complex salt is itself a potential ligand and can displace a ligand, which can then become the counter ion. Next is solvate isomerism. This form of isomerism is known as the hydrate isomerism. In case where water is involved as a solvent, this is similar to ionization isomerism. Solvate isomers differ by whether or not a solvent molecule is directly bonded to the metal ion or merely present as free solvent molecules in the crystal lattice. An example is provided by the aqua complex CrH2O6Cl3, which is violet in color, and its solvate isomer CrH2O5Cl2.H2O, which is grey green in color. Next is bonding in coordination compounds. Werner was the first to describe the bonding feature in coordination compounds, but his theory could not answer the basic questions like why only certain element possesses the remarkable property of forming coordination compounds, why the bonds in coordination compounds have directional properties, why coordination compounds have characteristic magnetic and optical property. Many approaches have been put forth to explain the nature of bonding in coordination compounds. Valence bond theory, crystal field theory, ligand field theory, and molecular orbital theory. We shall focus our attention on elementary treatment on the application of VBT and CFT to coordination compounds. VBT. According to this theory, the metal atom or ion under the influence of ligand can use its n-1d NSNP or NSNP-ND orbital for hybridization to yield a set of equivalent orbital of definite geometry such as octahedral, tetrahedral, square planar, and so on. These hybridized orbitals are allowed to overlap with ligand's orbital that can donate electron pair for bonding. It is usually possible to predict the geometry of a complex from the knowledge of its magnetic behavior on the basis of VBT. In the dimagnetic octahedral complex CONH363 positive, the cobalt ion is in +3 oxidation state and has the electronic configuration 3d6. The hybridization scheme is shown in the diagram. 6 pair of electrons, one from each ammonia molecule, occupy the 6 hybrid orbital. Thus the complex has octahedral geometry and is dimagnetic because of the absence of unpaired electron. In the formation of this complex, since the inner d orbital, that is 3d, is used in hybridization, the complex is called an inner orbital or low spin or spin paired complex. The paramagnetic octahedral complex COF63 negative uses outer orbital, that is 4d in hybridization, that is sp3d2. It is thus called outer orbital or high spin or spin free complex. Thus, in tetrahedral complexes, 1s and 3p orbital are hybridized to form 4 equivalent orbitals oriented tetrahedrally. In square planar complexes, the hybridization involved is dsp2. An example, NiCN42 negative. Here, nickel is in +2 oxidation state and has electronic configuration 3d8. Each of the hybridized orbital received a pair of electrons from a cyanide ion. The compound is dimagnetic as evident from the absence of unpaired electron. It is important to note that the hybrid orbital do not actually exist. In fact, hybridization is a mathematical manipulation of wave equation for the atomic orbitals involved. Next topic is magnetic property of coordination compounds. The magnetic moment of coordination compound can be measured by the magnetic susceptibility experiment. The result can be used to obtain information about the number of unpaired electrons and hence structures adopted by metal complexes. A critical study of the magnetic data of coordination compound of metal of the first transition series reveals some complications. For metal ions with up to 3 electrons in the d orbital, 2 vacant d orbital are available for octahedral hybridization with 4s and 4p orbital. The magnetic behavior of these free ions and their coordination entities is similar. When more than 3d electrons are present, the required pair of 3d orbitals for octahedral hybridization is not directly available. Thus, for d4, d5, d6 cases, a vacant pair of d orbital result only by pairing of 3d electrons, which leaves 2, 1 and 0 unpaired electrons respectively. The magnetic data agree with maximum spin pairing in many cases, especially with coordination compound containing d6 ion. However, with species containing d4 and d5 ions, there are complications. Next is limitations of valence bond theory. While the VBT to a larger extent explain the formation, structure and magnetic behavior of coordination compound, it suffers from the following shortcomings. It involves a number of assumptions. It does not give quantitative interpretation of magnetic data. It does not explain the color exhibited by the coordination compound. It does not give a quantitative interpretation of the thermodynamic or kinetic stability of coordination compound. It does not make exact prediction regarding the tetrahedral and square planar structure of 4 coordinate complexes. It does not distinguish between weak and strong field ligand. Next is crystal field theory. The CFT is an electrostatic model which considers the metal ligand bond to be ionic, arising purely from electrostatic interaction between the metal ion and the ligands. Ligands are treated as point charge in case of anions or point dipole in case of neutral molecule. The 5d orbital in an isolated gaseous metal atom have same energy, that is, they are degenerate. This degeneracy is maintained if a spherical symmetrical field of negative charges surround the metal atom. However, when this negative field is due to ligands in a complex, it becomes asymmetrical and the degeneracy of the d orbital is lifted. It results in splitting of the d orbital. The pattern of splitting depends upon the nature of the crystal field. Let us explain the crystal field splitting in octahedral coordination entity. In an octahedral coordination entity with 6 ligands surrounding the metal atom, there will be repulsion between the electrons in metal d orbital and the electrons of the ligands. Such a repulsion is more when the metal d orbital is directed towards the ligand and then when it is away from the ligand. Thus, the dx square minus y square and dz square orbital, which point toward the axis along the direction of the ligand, will experience more repulsion and will be raised in energy, and the dxy, dyz, and dxz orbital are directed between the axes will be lowered in energy relative to the average energy in the spherical crystal field. Thus, the degeneracy of the d orbital has been removed due to ligand electron metal repulsion in the octahedral complex to yield 3 orbital of lower energy T2G set and 2 orbital of higher energy EG set. The splitting of the degenerating levels due to the presence of ligands in a definite geometry is termed as crystal field splitting, and the energy separation is denoted by del naught. Thus, the energy of 2 Eg orbitals will increase by 3 by 5 del O, and that of 3 T2G will decrease by 2 by 5 del O. The crystal field splitting del O depends upon the field produced by the ligand and the charge on the metal ion. Some ligands are able to produce strong field, in which case the splitting will be large, whereas others produce weak field and consequently result in small splitting of d orbital. In general, ligand can be arranged in a series in the order of increasing field strength as given below. I negative, Br negative, SCN negative, Cl negative, S2 negative, F negative, OH negative, C2O42 negative, H2O, NCS negative, EDTA4 negative, ammonia, En, Cn, and Co. Such a series is termed as spectrochemical series. Let us assign electron in the d orbital of metal ion in octahedral coordination entity. Obviously, the single d electron occupy one of the lower energy T2G orbital in d2 and d3 coordination entity. The d electron occupy the T2G orbital singly in accordance with the Hund's rule. For d4 ions, two possible patterns of electron distribution arise. First, the fourth electron could either enter the T2G level and pair with an existing electron. Second, it could avoid paying the price of the pairing energy by occupying the EG level. Which of these possibilities occur depends on the relative magnitude of the crystal field splitting del O and the pairing energy P. The two options are: if del O is less than P, the fourth electron enter one of the EG orbital, giving the configuration T2G3 EG1. Ligand for which del O is less than P are known as weak field ligand and form high spin complexes. If del O is greater than P, it becomes more energetically favorable for the fourth electron to occupy T2G orbital with configuration T2G4 EG0. Ligands which produce this effect are known as strong field ligand and form low spin complexes. Next, crystal field splitting in tetrahedral coordination entity. In tetrahedral entity formation, the d orbital splitting is inverted and is smaller as compared to the octahedral field splitting. For the same metal, the same ligand and metal ligand distance, it can be shown that del T is 4 by 9 del O. Consequently, the orbital splitting energy are not sufficient large for forcing pairing, and therefore low spin configuration are rarely observed. The G subscript is used for the octahedral and square planar complexes which have center of symmetry. Since tetrahedral complex lacks symmetry, G subscript is not used with energy level. Next is color in coordination compounds. In the previous unit, we learned that one of the most distinctive property of transition metal complex is their wide range of colors. This means that some of the visible spectrum is being removed from white light as it passes through the sample, so the light that emerges is no longer white. The color of the complex is complementary to that which is absorbed. The complementary color is the color generated from the wavelength left over. If green color is absorbed by the complex, it appears red. The color of the coordination compound can be readily explained in terms of the CFT. Consider, for example, the complex TiH2O63 positive, which is violet in color, is an octahedral complex where the single electron Ti3 positive is a 3d1 system. In the metal, d orbital is in the T2g level in the ground state of the complex. The next higher state available for the electron is the empty Eg level. If light corresponding to energy of blue-green region is absorbed by the complex, it would excite the electron from T2g level to Eg level. Consequently, the complex appears violet in color. CFT attributes the color of the coordination compounds to DD transition of the metal. It is important to note that in the absence of metal, crystal field splitting does not occur and hence the substance is colorless. Next is limitation of CFT. The crystal field model is successful in explaining the formation, structure, color of the magnetic property of coordination compounds to a large extent. However, from the assumptions that the ligands are point charge, it follows that anionic ligands should exert the greatest splitting effect. The anionic ligand actually are found at the low end of the spectrochemical series. Further, it does not take account into the covalent character of bonding between the ligands and the central atom. These are some of the weaknesses of CFT, which are explained by LFT and MOT, which are beyond the scope of the present study. Next topic is bonding in metal carbonyls. The homoleptic carbonyls are formed by most of the transition metal. These carbonyls have simple well-defined structure. Tetracarbonyl nickel 0 is tetrahedral. Pentacarbonyl iron 0 is trigonal bipyramidal, while hexacarbonyl chromium 0 is octahedral. Decacarbonyl dimanganese 0 is made up of two square pyramidal MnCO5 unit joined by a Mn-Mn bond. Octacarbonyl dicobalt 0 has a CO-CO bond bridged by two CO groups. The metal carbon bond in metal carbonyl possess both sigma and pi character. The metal carbon sigma bond is formed by the donation of lone pair of electrons on the carbonyl carbon into a vacant orbital of the metal. The MC pi bond is formed by the donation of pair of electron from a ligand d orbital of metal into the vacant antibonding pi star orbital of carbon monoxide. The metal to ligand bonding creates a synergic effect which strengthens the bond between CO and the metal. Importance and application of coordination compounds. Coordination compound found use in many qualitative and quantitative chemical analysis. The familiar color reaction given by metal ions with a number of ligands as a result of formation of coordination entity form the basis for their detection and estimation by classical and instrumental methods of analysis. Hardness of water is estimated by simple titration with Na2EDTA. The Ca2 positive and Mg2 positive ions form stable complexes with EDTA. The selective estimation of these ions can be done due to difference in stability constant of calcium and magnesium ions. Coordination compounds are of great importance in biological system. The pigment responsible for photosynthesis, chlorophyll, is a coordination compound of magnesium. Hemoglobin, the red pigment of blood, which acts as oxygen carrier, is a coordination compound of iron. Vitamin B12, cyanocobalamin, the anti-pernicious anemia factor, is a coordination compound of cobalt. Among the other compound of biological importance with coordinated metal ions are the enzymes like carboxypeptidase and a carbonic anhydrase. Coordination compounds are used as catalysts for many industrial processes. Example includes rhodium complex. Wilkinson catalyst is used for hydrogenation of alkenes. There is a growing interest in the use of chelate therapy in medicinal chemistry. An example is the treatment of problem caused by the presence of metals in toxic proportion in plants' animal system. Thus, excess of copper and iron are removed by the chelating ligand D-penicillamine and deciferoxime B via the formation of coordination compounds. EDTA is used in the treatment of lead poisoning. Some coordination compounds of platinum effectively inhibit the growth of tumors. Examples are cisplatin and related compounds. This is all about the chapter coordination compounds. Thank you.